Question number 1. In the binomial expansion of 1 subtract 8x to the p, where mod of x is less than an eighth and p is a positive constant, the sum of the coefficient of x and the sum of the coefficient of x squared is equal to the coefficient of x cubed. The coefficient of x squared is positive. You have to determine the value of p. We have 1 subtract 8x to the p, and using the binomial series formula for terms up to x cubed, we have the first term, which is 1. For the next term, we have p divided by 1 factorial multiplied by negative 8x to the 1. For the next term, we have p multiplied by p subtract 1 over 2 factorial multiplied by negative 8x squared. For the next term, we have p multiplied by p subtract 1 multiplied by p subtract 2 divided by 3 factorial multiplied by negative 8x cubed. And then we have higher order terms. So, simplifying, we have 1 subtract 8px plus 32p multiplied by p subtract 1 x squared subtract 256p times p subtract 1 times p subtract 2 over 3 x cubed plus higher order terms. We know that the sum of the coefficient of x and the coefficient of x squared is equal to the coefficient of x cubed. So we have negative 8p plus 32p multiplied by p subtract 1, which is equal to negative 256p multiplied by p subtract 1 multiplied by p subtract 2 over 3. If we divide each term by 8p, then we have negative 1 plus 4 multiplied by p subtract 1 equals negative 32 times p subtract 1 times p subtract 2 over 3. And now multiplying through by 3, we have negative 3 plus 12 times by p subtract 1 equals negative 32 times p subtract 1 times p subtract 2. So, we have negative 3 plus 12p subtract 12 equals negative 32 multiplied by p squared subtract 3p plus 2. So we have negative 3 plus 12p subtract 12 equals negative 32p squared plus 96p subtract 64. So we have 32p squared subtract 84p plus 49 equals 0. If we factorize, we have 4p subtract 7 multiplied by 8p subtract 7 equals 0, and therefore p equals 7 over 4, p equals 7 over 8. We know that the coefficient of x squared is positive, and you will recall that 32p multiplied by p subtract 1 is the coefficient of x squared. So we have 32p multiplied by p subtract 1 is greater than 0. So p subtract 1 is greater than 0, meaning p is greater than 1. So we have p equals 7 over 4 only, and that's because 7 over 8 is less than 1, whereas 7 over 4 is greater than 1. So we have p equals 7 over 4. Question number 2. Figure 1 shows the curve defined by the equation y squared plus 3y subtract 6 sin y equals 4 subtract x squared. The point P, with coordinates xy lies on the curve. The distance from the origin O to P is d. Part A, write down an equation for d squared in terms of y only. Here we've got some point P which lies on this curve. The distance from O to P is d. From this we can form a right-angled triangle. We have a horizontal distance of x and a vertical distance of y. Using Pythagoras, d squared will equal x squared plus y squared. So, what we need to do is rewrite this equation in terms of y only. Now, using this equation, which I will call equation 1, we can rearrange for x squared and substitute into this equation, which I will call equation 2. From equation 1, we have x squared, which is equal to 4, subtract y squared, subtract 3y, plus 6 sine y, and I will call this equation 3. So then, I will substitute in equation 3 into equation 2. So we have d squared equals, now for x squared we have what we have here, which is 4 subtract y squared, subtract 3y plus 6 sine y, plus y squared. So we have d squared equals 4 subtract 3y plus 6 sine y. Part B, hence determine the minimum value of d, giving your answer in simplest form. For part B, we need to minimize d squared to find the minimum value of d, which means we need to differentiate with respect to y d squared. And so, differentiating with respect to y, we end up with negative 3 plus 6 cos y. And so, setting d squared over dy equal to 0, we have negative 3 plus 6 cos y equals 0. So cos y equals 0.5, from which we can see y is equal to plus minus pi over 3. And with these values of y, we need to substitute these back into the equation shown here to find out the minimum value of d squared, and from that we can find out the minimum value of d. So when y equals pi over 3, we have d squared, which is equal to 4 subtract 3 times by pi over 3 plus 6 times by the sine of pi over 3. So we have 4 subtract pi plus 6 times by root 3 over 2, which is equal to 4 subtract pi plus 3 root 3. And if we square root, you will find d to equal the square root of 4 subtract pi plus 3 root 3. Now when y equals negative pi over 3, we have d squared, which is equal to 4 subtract 3 times by negative pi over 3, subtract 6 sine of negative pi over 3. So we have 4 plus pi subtract 6 times by root 3 over 2. So we end up with 4 plus pi subtract 3 root 3. And if we square root, you will find d to equal the square root of 4 plus pi subtract 3 root 3. And so for us to state the minimum value of d, we need the smaller value of d, and that's the one shown here. So d min is equal to the square root of 4 plus pi subtract 3 root 3. Question number 3. For the first part, determine the value of k such that the arctan of 1/2 subtract the arctan of 1/3 is equal to the arctan of k. Given the equation, we can take the tan of both sides to find out what k is. k will equal the tan of the arctan of a half subtract the arctan of 1/3. Now, on the right hand side of this equation, we can use the identity for tan of a subtract b. The tan of a subtract b is equal to the tan of a subtract the tan of b over 1 plus the tan of a times the tan of b. And here, a is equal to the arctan of a half, and b is equal to the arctan of 1/3. And so, k will equal the tan of the arctan of a half subtract the tan of the arctan of 1/3 over 1 plus the tan of the arctan of a half times by the tan of the arctan of 1/3. Recognizing that the tan of the arctan of a half is just a half, and the tan of the arctan of 1/3 is just a third, we end up with a half subtract a third over 1 plus a half times by a third. So for the numerator we have a sixth, for the denominator we have 1/7. We end up with 7/6. For part A of the second part of the question, we have to prove that cos of 3a is equivalent to 4 cos a cubed subtract 3 cos a. The cos of 3a we can rewrite as cos of 2a plus a, and using the identity for cos of x plus y, we can rewrite this as cos of 2a multiplied by cos a subtract sine of 2a multiplied by sine a. Now the cos of 2a, we can replace that with 2 cos squared a subtract 1, we still multiplied by the cos a, and the sine 2a, we can write that as 2 sine a cos a, and then we still multiply by the sine a. Expanding the brackets, we have 2 cos squared a times by cos a, which is 2 cos cubed a. Negative 1 times by cos a is negative cos a. And then we have negative 2 sine a times sine a times by cos a, which is negative 2 sine squared a cos a. And what we can now do is replace the sine squared with 1 minus cos squared. So we have the result shown here, and don't forget we still need to multiply by cos a. Now expanding and simplifying, we have 2 cos cubed a subtract cos a subtract 2 cos a plus 2 cos cubed a, which simplifies to 4 cos cubed a subtract 3 cos a. Given that a equals cos of 20 degrees, part B, write down in terms of a an expression for cos of 40 degrees. For part B, if a is equal to cos 20 degrees, then cos 40, we can rewrite that as cos of 2 times by 20 degrees, and using 2 cos squared a subtract 1, we can rewrite this as 2 cos squared of 20 degrees subtract 1, so we have 2a squared subtract 1. Part C, determine in terms of a simplified expression for cos 80 degrees. For cos 80 degrees, we can write that as cos of 2 times by 40 degrees. So we have 2 cos squared of 40 degrees subtract 1, and we already know what cos of 40 degrees is, that's 2a squared subtract 1. So we have 2 multiplied by 2a squared subtract 1 squared subtract 1. So we have 2 multiplied by 4a to the 4 subtract 4a a squared plus 1, subtract 1. So we end up with 8a to the 4, subtract 8a squared plus 1. Part D, use part A to show that 4a cubed subtract 3a equals 1/2. For part D, we have to use part A with cos of 20 degrees equaling a. Now, cos of 3 times by 20 degrees will equal cos of 60 degrees. And if we go to part A, we know that the cos of 3a is equal to 4 cos cubed a subtract 3 cos a. We have 4 cos cubed 20 degrees, subtract 3 cos 20 degrees equals cos 60 degrees. So we have 4a cubed subtract 3a equals cos of 60 degrees, which is 1/2. So therefore, this is the result we wanted to show. Part E, hence or otherwise, show that cos of 20 degrees times cos of 40 degrees times cos of 80 degrees is equal to 1/8. So we've got cos of 20 times cos of 40 times cos of 80. We know that cos of 20 is a, we know that cos of 40 is 2a squared subtract 1, and we know cos of 80 is 8a to the 4 subtract 8a squared plus 1. Multiplying the first two brackets together, we end up with 2a cubed subtract a, multiplied by 8a to the 4 subtract 8a squared plus 1. Now, if we expand the brackets, we've got this term times by this term, which gives us 16a to the 7. Then we've got this term times by this term, which gives us negative 16a to the 5. Then we've got this term times by this term, which gives us 2a cubed. Then we've got this term times by this term, which gives us negative 8a to the 5. This term times by this term, which gives us 8a cubed. Then we've got this term times by this term, which gives us negative a. And if we collect like terms and simplify, we end up with 16a to the 7, subtract 24a to the 5, plus 10a cubed, subtract a. We can now factorise out an a from each of these terms, so we've got a multiplied by 16a to the 6, subtract 24a to the 4, plus 10a squared, subtract 1. Somehow, we need to use what we found in part D. In other words, we need to somehow figure out how we can use this 4a cubed subtract 3a equals 1/2. Now, what you will notice is if I take this 4a cubed subtract 3a and square it, I end up with 16a to the 6 subtract 24a to the 4 plus 9a squared. It's almost what we have here. So we can rewrite this result in terms of what we've just written here. So we have a multiplied by 16a to the 6 subtract 24a to the 4 plus 9a squared. Now, we want to go from 9a squared to 10a squared, and then we still have the negative 1. So we can add a squared and subtract 1. So all this is the same as what we have here. So we have a multiplied by. Now, the result shown in orange here is just 4a cubed subtract 3a squared. And then we add on a squared subtract 1. And 4a cubed subtract 3a, that's equal to 1/2. So we have a multiplied by 1/2 squared plus a squared subtract 1. So we've got a multiplied by a squared subtract 3/4. We have a cubed subtract 3/4 a. And if I factorise out a 1/4, we have 1/4 multiplied by 4a cubed subtract 3a. And we know that 4a cubed subtract 3a is 1/2. So we've got 1/4 times by 1/2, which is equal to 1/8. And that is the result of cos of 20 times cos of 40 times cos of 80. Part B, use the substitution x equals 3u plus 3 over u subtract 3 to determine the exact value of I, where I is equal to the integral from 1 to negative 3 of the natural log of 3 subtract x over 3 plus x squared with respect to x, giving your answer in simplest form. So we've got x equals 3u plus 3 over u subtract 3. What we need to do is differentiate this result. So if I let f equal 3u plus 3, f dash will equal 3, and if I let g equal u subtract 3, g dash will equal 1. And so using the quotient rule, x dash will equal 3 multiplied by u subtract 3, subtract 1 times by 3u plus 3 over u subtract 3 squared. So we've got 3u subtract 9 subtract 3u subtract 3 over u subtract 3 squared. And we end up with negative 12 over u subtract 3 squared. And from this we can state that dx will equal negative 12 over u subtract 3 squared du. If we go back to the question, you will notice we have limits in terms of x. We've got the lower limit, which is negative 3, and the upper limit, which is 1. So we need to find the corresponding u limits. When x equals negative 3, we've got negative 3 equals 3u plus 3 over u minus 3. So we've got negative 3 multiplied by u minus 3 equals 3u plus 3. Negative 3u plus 9 equals 3u plus 3. 6u equals 6, so u equals 1. And this is the lower limit. And for the upper limit, that's when x equals 1. We have 1 equals 3u plus 3 over u subtract 3. So we've got 1 times by u subtract 3 equals 3u plus 3. So we've got u subtract 3 equals 3u plus 3. 2u equals negative 6, so u equals negative 3. And this is our upper limit. Now here is what our integral is, and we need to replace correspondingly and rewrite this in terms of u. So the integral becomes the following. We've got the integral, and then our lower limit is 1 and our upper limit is negative 3. We've got the natural log of 3 subtract x. We've got the natural log of 3 subtract 3u plus 3 over u subtract 3 over 3 plus x squared. So we've got 3 plus 3u plus 3 over u subtract 3 squared multiplied by dx, and we know what dx is. That's negative 12 over u subtract 3 squared du. Now we can rewrite this natural log. If we put this over a common denominator of u subtract 3, we've got 3 times u subtract 3, subtract 3u plus 3 over u subtract 3. And we can rewrite the denominator as 3 plus 3u plus 3 squared over u subtract 3 squared. And we multiply this by negative 12 over u subtract 3 squared du. So let's simplify. We've got the natural log of 3u subtract 3 subtract 3u subtract 9 over u subtract 3, and if I multiply through by u subtract 3 squared, I've got 3 times by u subtract 3 squared plus 3u plus 3 squared multiplied by negative 12 du. So we've got the natural log of negative 12 over u subtract 3 over, well here we've got 3 times by u squared subtract 6u plus 9 plus 9u squared plus 18u plus 9 multiplied by negative 12 du. So the numerator remains the same, and for the denominator I've got 3u squared subtract 18u plus 27 plus 9u squared plus 18u plus 9 multiplied by negative 12 du. So I've got this integral, I've got the natural log of 12 over 3 subtract u over 12u squared plus 36 multiplied by negative 12 du. So if I take the negative out and write the integral symbol, and then recognise that 12 over 12u squared plus 36 can be simplified, I'd have the natural log of 12 over 3 subtract u over u squared plus 3 du. So I've got negative integral of the natural log of 12 subtract the natural log of 3 subtract u. That's the same as the natural log of 12 over 3 subtract u, so I've just used the subtraction law of logs there, divided by u squared plus 3 du. Now, if I've got negative and then an integral, what I can do is remove this negative and swap the limits. So I've got the integral from negative 3 to 1, and then I've got the natural log of 12 subtract the natural log of 3 subtract u over u squared plus 3 du. And we can split this up. We've got this integral of the natural log of 12 over u squared plus 3 subtract the natural log of 3 subtract u over u squared plus 3 du. So I've got the integral of the natural log of 12 over u squared plus 3 du subtract the integral of the natural log of 3 subtract u over u squared plus 3 du. And what you will find, if we go back to the question, this is exactly what we have here, but instead of an x we've got a u. So recognizing this is the same as the question, but we use a u instead of an x, and recognizing that this is equal to I, the original integral I, which is all of this result, so I equals all of this, we have I equals the integral of the natural log of 12 over x squared plus 3 dx subtract I, which is this bit. So this bit is what I is. So we've got I, which is all of this, and recognizing this is exactly what the question's asking us to find, we would have I equals the integral from negative 3 to 1 times the natural log of 12 over x squared plus 3 dx subtract I. So we've got 2I equals the integral of the natural log of 12 over x squared plus 3 with respect to x from negative 3 to 1. And if I divide through by 2, I equals a half times by the integral of the natural log of 12 of x squared plus 3 with respect to x from negative 3 to 1. And what I can do is factorize out a natural log of 12. So I've got the natural log of 12 times by a half, which is natural log 12 over 2, times by this integral here. And what you will find here is this is exactly what we worked out in part A of the question. And we found that to equal root 3 over 3 times by the arctan of root 3 over 3x plus c. So we've got the natural log of 12 over 2 times by root 3 over 3 times by the arctan of root 3 over 3x in between 1 and negative 3. And so if I multiply the natural log of 12 over 2 times root 3 over 3, we can rewrite this as root 3 times the natural log of 12 over 6 times the arctangent of root 3 over 3x, and we want to evaluate this between negative 3 and 1. So, substituting in 1 for the upper limit, we've got the result shown here, and substituting in negative 3 for the lower limit, we've got the result shown here. So, we've got root 3 times the natural log of 12 over 6, and the arctan of root 3 over 3, that's just pi over 6, and we subtract from this root 3 times the natural log of 12 over 6, and the arctangent of negative root 3 that will equal negative pi over 3. And if I factorise out in root 3 times the natural log of 12 over 6, inside the bracket would have pi over 6 plus pi over 3. Notice we've got the minus and the minus, which give the plus. And pi over 6 plus pi over 3, that is pi over 2. So I've got root 3 times the natural log of 12 over 6 times by pi over 2, and therefore this would simplify to root 3 pi times the natural log of 12 over 12. Question number 5. Figure 2 shows a sketch of a hexagon OABCDE where the interior angle at O and at C are each 60 degrees. The interior angle at each of the other vertices is 150 degrees. OA equals OE equals BC equals CD. AB equals ED equals 3 times by OA. Given that the vector OA is equal to A and the vector OE is equal to E, for part A we have to determine the vector AB. So for part A, let's draw this triangle here where AM is what OE is. So we go up and then down. Directly underneath A, vertically, I've got this point W, and the length of OA is equal to mod A, and the same thing applies for AM. We've got 60 degrees here, 30 degrees here, and 30 degrees here, because we've got a line of symmetry at AW. And this OM will be parallel to AB. So essentially we've just drawn this triangle here, and this is parallel to AB. The vector AB then will equal to lambda times by A plus E. Now this A plus E is what the vector OM is, because we go O to A and then A to M. And A to M is sort of going back down, and that's given by the vector E. Which means the mod of the vector AB is equal to lambda times by A plus E. And we also know that AB is equal to 3 times OA. So the mod of AB is equal to 3A. OM, that's given by 2 times by OW, because this is the midpoint of OM. And if I think of a right angled triangle, OM will equal 2 times by mod A times by cos 30. So continuing to work this out, we've got root 3A. And that's because cos 30 is equal to root 3 over 2. So I've got 2 times by root 3 over 2, which is just root 3. And as we've said before, OM is equal to A plus E. So if I take the mod of this, the mod of A plus E that will equal root 3A, which is what we found here. So we also need to recognize that the mod of AB is equal to 3 times by mod A. So we have 3 times by mod A equals lambda times by root 3 times by mod A, which means we can find out what lambda is. So lambda is equal to 3 over root 3, which is root 3. And knowing that, we can then state what AB is. AB will equal root 3 times by A plus E. And this is of course equal to ED. Now for part B, we have to determine our simplified expressions in terms of A and E, the vector OD. So we want to go from O to D. And the way we can do that is we can go from O to E and then E to D. So OD is equal to OE plus ED. Now we know what OE is, that's just E. And ED, that is what we've just worked out here, root 3 times by A plus E. So let's simplify. We have root 3A plus root 3 plus 1 E. The point R divides AB internally in the ratio 1 to 2. Part C, determine the vector RC as a simplified expression in terms of A and E. So what this is saying is we've got some point R on this line here, and we need to go from R to C. So we can go from R to B and then B to C, and that will be the vector RC. So RB will equal 2/3 times by AB, and that's because we've got the ratio 1 to 2. Now the vector AB we've worked out here. So we've got 2/3 times by root 3 A plus E. Now going from R to C then, we have to go from R to B and then B to C. So we've got RB, which is 2/3 times by root 3 times A plus E, plus BC. So we need to go from B to C, and this will equal the vector E. And so we end up with 2 root 3 over 3A plus 2 root 3 over 3 plus 1 E. The line through the points R and C meet the line through the points O and D at the point X. We have to determine the vector OX in the form lambda A plus mu E, where lambda and mu are real values in simplest form. Let's begin by showing that on a diagram. We've got the line shown in red and the line shown in blue, which meet at the point X. Now, there's two ways of going from O to X. We can go O to A to R, and then R to X. Or we can go from O to D, and then D to X. Now, what you will recognize for the red line, the vector RC is a multiple of Rx, because R, C and X line a straight line, and similarly the vector OD is a multiple of OX, and that's because OD and X line a straight line. So the first way to go from O to X, we can go from O to A, then A to R, then R to X, and we need to recognize that RC is a multiple of Rx. So we have P multiplied by RC. So we have OA, which is A. Now R lies on AB, and we know that the ratio of AR to RB is 1 to 2. So AR is 1/3 of AB, and we know that this vector AB is equal to √3 times by A plus E. And then we have P times by RC, and here is what RC is. That's 2√3/3A plus 2√3/3 plus 1E. So let's simplify and tidy this up. In terms of the A's, we would have 1 plus √3/3 plus 2√3p/3a, and in terms of the E's, we have √3/3 plus 2√3p/3 plus p e. The second way from going from O to X is through OD, and we need to recognize that OD is a multiple of OX because it lies in a straight line. So OX is equal to Q, some factor, of OD. Now, OD, we can go from O to D by going from O to E, and we know that vector, and then E to D, and we also know that vector because we worked it out earlier, and that was here. So we have Q times by OE plus ED. So we've got Q times by, now here we've got E plus √3 times A plus E. And if we simplify, we've got √3QA plus √3 plus 1QE. What we now need to do to find out what P and Q are is compare the coefficients of A and E. And that's because these two vectors are the same. So if I compare coefficients by comparing the A first, I've got what I found in way 1, which was 1 plus √3/3 plus 2√3p/3, and this will equal √3q. I'll call this equation 1. And if I compare the E's, I've got √3/3 plus 2√3p/3 plus p, which is what I had here, equals √3 plus 1 q. I will call this equation 2. Now, what I can do is divide equation 1 by √3, and in doing so, I've got 1 over √3 plus 1/3 plus 2p/3, which is equal to q. So q will equal √3 plus 1 plus 2p/3. I'll call this equation 3. And now I will substitute in equation 3 into equation 2, and that will eliminate this q. So I've got √3 plus 2√3p/3 plus p, which is equal to √3 plus 1 multiplied by q, and here is what q is. That's √3 plus 1 plus 2p all over 3. Now, let's multiply through by 3. So I've got √3 plus 2√3p plus 3p equals √3 plus 1 times by √3 plus 1 plus 2p. If I simplify the right hand side, I've got 3 plus √3 plus 2√3p plus √3 plus 1 plus 2p. Simplifying even further, I've got √3 plus 3p equals 4 plus 2√3 plus 2p, which means p is equal to 4 plus √3. And knowing what q is, we can now find out what q is. That's √3 plus 1 plus 2 times by p, which is 4 plus √3, all over 3. And if I simplify this, I get 3√3 plus 9 over 3, which simplifies even further to √3 plus 3. So that's what q is. And I know that the vector OX is equal to q times by OD. So that will also equal from way 2 root 3 q a plus root 3 plus 1 q e. So I can replace the q with what I've just found here. So I've got OX, which is equal to root 3 times by root 3 plus 3 a plus root 3 plus 1 multiplied by root 3 plus 3 e. So if I simplify for the a's, I've got 3 plus 3 root 3a, and if I simplify for the e's, I've got 4 root 3 plus 6e, and that's what OX is. Question number 6. Figure 3 shows a block A with mass 4m and a block B with mass 5m. That's shown here and here. Block A is at rest on a rough plane inclined at an angle alpha to the horizontal. Block B is at rest on a rough plane inclined at an angle beta to the horizontal. The blocks are connected by a light inextensible string which passes over a small smooth pulley at the top of each plane. A small smooth ring C of mass am is threaded on the string between the pulleys so that A, B and C all lie in the same vertical plane. The part of the string between A and its pulley lies along a line of greatest slope of the plane of angle alpha. The part of the string between B and its pulley lies along a line of greatest slope of the plane of angle beta. The angle between the vertical and the string between each pulley and the ring C is gamma. The two blocks A and B are modelled as particles. Given that tan alpha equals 5 over 12, tan beta equals 7 over 24, and tan gamma equals 3 over 4, the coefficient of friction, mu, is the same between each block and its plane. One of the blocks is on the point of sliding up its plane. The tension in the string is T. Part A, determine in terms of m and g an expression for T. If we know that tan alpha is 5 over 12, tan beta is 7 over 24, and tan gamma is 3/4, what we can do is find out what sine alpha, cos alpha and tan alpha are, and similarly we can find out what sine beta, cos beta, tan beta are, and we can find out what sine gamma, cos gamma and tan gamma are. And for that I've constructed right-angled triangles as shown. Sine alpha is 5 over 13, cos alpha is 12 over 13, and tan alpha is 5 over 12. Sine beta is 7 over 25, cos beta is 24 over 25, tan beta is 7 over 24. Sine gamma is 3/5, cos gamma is 4/5, and tan gamma is 3/4. So if we look at C first, we've got the tension here, and we've got a tension here, and then we've got the weight, which is given by AMG. If I look at A, we've got the tension pulling up, we've got the reaction force, we'll call that RA, and we've got the weight 4mg. And if we take a look at B, we've got the tension going up, the reaction force RB, and the weight 5mg. Now the blocks are sliding up, and that's because this AMG is greater than the 4mg, and the AMG is also greater than the 5mg. And we know that the planes are rough, which means here we've got a friction force FA going down, and here we've got a friction force FB also going down. For us to find the tension, what we can do is resolve vertically at C. So, if I resolve vertically, I've got T cos gamma plus another T cos gamma, which is equal to AMG. So I've got 2T cos gamma, which is equal to AMG, and I know what cos gamma is, that's equal to 4/5. So I've got 2T times by 4/5, which is equal to AMG, meaning T is equal to 5mg. Part B, draw a diagram showing the forces on block A, clearly labelling each of the forces acting on the block. Well, that's what we've done over here. So for part B, see figure 3. Part C, we have to determine the value of mu, giving a justification for your answer. Well, the way we will do this is we will look at block A and block B separately. So, if we take a look at block A, let's resolve parallel to the plane. So resolving parallel, we've got T going up and then we've got the weight component going down, and we've also got the friction force going down, and that will all equal 0 because it's in equilibrium. So we've got T subtract 4mg sine alpha, which is equal to Fa. And we know what sine alpha is. That's given by 5 over 13. So we've got 5mg take away 4mg times 5 over 13 equals Fa. So Fa will equal 45 mg over 13. Let's now resolve perpendicular. Resolving perpendicular, we've got Ra going up and we've got a component of the weight going down. So we've got Ra equals 4mg cos alpha. And we know what cos alpha is, that's 12 over 13. So we've got 4mg times by 12 over 13. Now, if we simplify this, we get 48 mg over 13. If A is about to slip, that means Fa is equal to mu A times by Ra. We know what Fa is, we know what Ra is, so we've got 45 mg over 13 equals mu A times by 48 mg over 13, and therefore mu A is equal to 15 over 16. So in other words, for A to stay still, mu has to be greater than or equal to 15 over 16. Let's now look at block B. It's exactly the same thing. We need to resolve parallel, then perpendicular to the plane. So, resolving parallel, we've got T subtract 5 mg sine beta equals Fb. And we know what sine beta is. We worked that out to be 7 over 25. So we've got 5 mg take away 5 mg times by 7 over 25 equals Fb, meaning Fb is 18 mg over 5. And if I resolve perpendicular, I've got Rb equals 5 mg cos beta. I know what cos beta is. That's equal to 24 over 25. And substituting those in, you will find Rb to equal 24 mg over 5. And now, if B is about to slip, Fb is equal to mu B times Rb. So, we know what Fb is, we know what Rb is. We've got 18 mg over 5 equals mu times by 24 mg over 5. So we've got mu B, which is equal to 3/4, and therefore for B to stay still, mu has to be greater than or equal to 3/4. So if I compare this 3/4 to the 15 over 16, A needs more friction than B to stop it sliding up the plane, which means mu is equal to 15 over 16 only. Now, if we had mu equaling 3/4, finding out what Fa is, that will equal 3/4 times by 48 mg over 13, which is 36 mg over 13. This, if I compare the 36 mg over 13 with the 45 mg over 13, this value is smaller, so it's not at the maximum. In other words, it's not at the point of slipping, and in this case the system wouldn't move. So mu will equal 15 over 16 only. Question number 7. Figure 4 shows a circle with radius r1 and a circle with radius r2. The circles touch externally at a single point above the x-axis. Both circles also have the x-axis as a tangent, and that's what we see here. Part A, we have to show that the horizontal distance between the centres of the circles D is given by d squared equals 4r1 r2. Now, the distance between the centres is shown here. That's r1 plus r2. We've got a distance of r1 to here and a distance of r2 to here. We've got this horizontal line, and the distance here will be given by d, and the vertical distance, well, that will be the difference between r1 and r2, as shown here. So if we use Pythagoras, we've got r1 take away r2 squared plus d squared equals r1 plus r2 squared. And if we rearrange, you will see that d squared equals r1 plus r2 all squared take away r1 take away r2 squared. So if we expand the brackets, we'd have r1 squared plus 2r1 r2 plus r2 squared. And then we subtract from this, r1 squared take away 2r1 r2 plus r2 squared, which gives us 4r1 r2. The finite region R, shown shaded in figure 4, is bounded by the x-axis and minor arcs of the two circles. And given that R1 is greater than or equal to R2, for part B we have to show that the area of R is given by R1 plus R2 times the square root of R1 R2 take away a half times R1 squared take R2 squared theta take away a half pi R2 squared, where cos theta equals R1 take R2 over R1 plus R2. So we've got the region R shown shaded here, and as before we've got the distance between the centres being R1 plus R2, we've got the radius of C1 being R1 and the radius of C2 being R2. Now, if we know that d squared equals 4r1 r2, then d will equal the square root of 4r1 r2, which is 2r1 r2. We'll show that here. Now, for us to find out this area R, we need to recognise we've got a trapezium, then we've got this sector from C1, and we've got another sector from C2. Now, what we know already is that this angle is theta. So that means this angle here, because we've got a right angled triangle, will be pi over 2 take away theta. And here we've got a pi over 2. So, for the area of the trapezium, we've got a half times by the sum of the two parallel sides, so that's the sum of the radius, so that's r1 plus r2, times by the height, which is this distance d, which is 2 times by square root r1 r2. And if we simplify this, we end up with r1 plus r2 times square root r1 r2. Now we've got this sector from the first circle. That will be given by a half r1 squared theta. Now for the second sector here, we've got a half times by r2 squared, and then we have to times by this total angle, which is a sum of pi over 2 take away theta added to the pi over 2. So the area of sector 2 is a half r2 squared times pi take away theta. So the area of R then will be the trapezium take away sector 1 take away sector 2. So we've got R1 plus R2 times square root R1 R2 take away a half R1 squared theta take away a half R2 squared times by pi take away theta. So now let's simplify. Well, this first term will remain as it is, the next term will remain as it is, and here I've got minus a half R2 squared times by pi, and then I've got minus a half R2 squared times by minus theta, which is positive a half R2 squared theta. So this term will remain as it is, And if I take away a half, and then I can factorize that out essentially, I'd have a half times by r1 squared, take away r2 squared, and times that by theta, and then I take away this term, which is a half r2 squared pi. And that's exactly what we wanted to show. The sequence of circles C1, C2, C3, etc. with radii R1, R2, R3, etc. respectively is constructed such that each circle is tangential to and above the x-axis. The first circle C1 has centre 0, 1. Each successive circle touches the preceding one externally at a single point. The horizontal distance between the centres of two successive circles form a geometric sequence with first term 2 and common ratio 1/√3. The first few circles in the sequence are shown in figure 5. So that's what we see here. We've got two circles, then we've got the next two circles, and then we've got the next two circles, and then the two circles after that. For the first part of part C, we have to determine the value of R3. So, C1 has a centre 0, 1, meaning R1 is given by 1. And we know that the horizontal distance between C1 and C2 is 2. So what we can do is use this formula for D, which is 2 times by square root R1, R2. So, we have 2 equals 2 times by square root of R1, which is 1, times by R2. And from this you can see R2 is equal to 1. Now, to find the distance between C2 and C3, we know already from the question we've got a first term of 2 and we've got a common ratio of 1/√3, meaning the distance between C2 and C3 will be given by 2 times by 1/√3, which is 2/√3. And again, if I use this formula, D equals 2 times by square root of R1, R2, I've got 2/√3 equals 2 times by the square root of 1 times by R3. And from this we can find out what R3 is. If I divide both sides by 2 and then square, and then rearrange, we'd have R3, which is equal to 1/3. For the next part of the question, we have to show that for n being greater than or equal to 1, Rn plus 2 is equal to k Rn, where k is a constant to be determined. So if the distance between Cn and Cn plus 1 is dn, and that will equal 2 times by the square root of Rn plus 1, and that's quite simply using this formula here, then the distance between Cn1 and Cn plus 2, that will be given by dn plus 1 equals 2 times by the square root of Rn plus 1 Rn plus 2. Now, what we would know is we've got this common ratio of 1/√3, meaning dn plus 1 equals 1/√3 dn. And we know what dn is, that's the result shown here. So we've got 1/√3 times by this 2 times by square root of Rn times Rn plus 1. So that's what dn plus 1 is. We can now equate these together. So we've got 2 times by the square root of Rn plus 1 Rn plus 2 equals 1/√3 times by 2 times square root of Rn plus 1. If we square both sides and cancel the 2's, we have Rn plus 1 Rn plus 2 equals 1/3 Rn plus 1, and the Rn plus 1's cancel from both sides, so we will be left with Rn plus 2 equals 1/3 Rn. For the third part, hence show that for n being greater than or equal to 1, R2n equals R2n minus 1. we know that R1 equals 1 and we know that R2 equals 1. So let's write that down. Now, what we can do is use this formula here to find out what R3 is. R3 will equal 1/3 R1. So here we've got n, here we've got n plus 2. And I know what R1 is, so I've got 1/3 times y1, which is 1/3. And R4 will equal 1/3 times by R2, again that's using this formula here. So I've got 1/3 times by 1, which is 1/3. R5, that will equal 1/3 times by R3, so I've got 1/3 times by 1/3, which is 1/9, and R6 is 1/3 times by R4, which is 1/3 times by 1/3, which is also 1/9. R7, that's going to be 1/3 times by R5, which is 1/3 times by 1/9, which is 1/27, and R8 is 1/3 times by R6, so we've got 1/3 times by 1/9, which is also 1/27. So what do we notice? Well, what we would notice for the radius is we've got odd and even ones. So for R odd, we've got R2n minus 1, and the reason we start off at 2n minus 1 instead of 2n plus 1 for odd terms is if I start off at 2n minus 1, that includes the first term. If I start off with 2n plus 1, well, when n is 1, I would start off at R3, so it misses out the R1 term. And what this will be given by is a geometric series. I've got 1, 1/3, 1/9, 1/27, etc. So I've got this 1 for my first term, and I times this by 1/3, which is the common ratio, to the power of n minus 1. So this is essentially the formula un equals a times by r to the power of n minus 1. And that 1/3 is the common ratio. So I'm left with 1/3 n minus 1. And for the even terms, I've got R2n, so I've got 1, which is again the first term, times by 1/3 n minus 1. And that simplifies to 1/3 n minus 1. Now these are equal. So I've got the R2n minus 1, which is equal to the R2n. And that's true for n being greater than or equal to 1. And that's exactly what we wanted to show. The region bounded between Cn plus 1 and the x-axis is Rn. The total area A bounded above the x-axis and under all the circles is the sum of the areas of all these regions. Part D, determine the value of A, giving the answer in simplest form. So if I go back to the question, you will see we've got the area R1, that's between C1 and C2. The area R2 is in between C2 and C3. The area R3 will be in between C3 and C4. The area R4 will be given between C4 and C5, etc. And this goes on. So essentially what we have is a sort of continuous area which we need to work out. In other words, the total area will be given by R1 plus R2 plus R3, etc. Rn is the area between Cn and Cn plus 1 on the x-axis, and we know for the radii we've got 1, 1, that's R1, R2, 1/3, 1/3, that's R3 and R4, and we can continue. Now, for the radius, we know we've got this common ratio of 1/3, and that's from here. You can think of this to be a length scale factor, and because we're concerned with areas, let's find the area scale factor by squaring this. The area scale factor will be 1/9, that's 1/3 squared. Now there's two situations we've got. We've got the situation where we've got equal radii, so that's C1 and C2, C3 and C4, C5 and C6, etc. And we've also got the situation where we don't have equal radius, so that's C2, C3, C4, C5, etc. So there's two cases we need to consider. And the way we do this question is to sort of think about the trapezium take away sector 1, take away sector 2, essentially. But the difference is you could have equal radii or radii which are not equal. So for equal radii, we've got R1, which is 1, and R2, which is 1. Now, if I go back to the question, we know that cos theta equals R1 take R2 over R1 plus R2. So, with that, we'd have cos theta here being 1 take away 1 over 1 plus 1. So that's the cos theta of 0. And if I find out what theta is, that's just pi over 2. So R1 will equal 1 plus 1 times by square root of 1 times by 1, take away a half times by 1 squared, take away 1 squared times by pi over 2, take away pi over 2 times by 1 squared. So essentially what we've done is the same thing that we did over here. We've got the trapezium, sector 1 and sector 2, where theta is pi over 2, essentially. So, if I simplify all this, what we end up with is 2 take away pi over 2. Now, the area R3, using our scale factor of 1/9, that's given by a 1/9 times by R1. So I've got a 1/9 times by 2 take pi over 2 for my area of R3. And remember, we're talking about equal radii here. So we've got R1, R3, then the next one will be R5. So R5 will equal a 1/9 times R3, so I've got a 1/9 times by a 1/9 times 2 take pi over 2, which is equal to 1 over 81 multiplied by 2 take pi over 2. Now here what we have a geometric sequence. We've got the first term and the common ratio. The first term is 2 take pi over 2 and the common ratio is 1/9. So the sum of R odd then will equal the first term, A, which is 2 take pi over 2, over 1 take away a 1/9. So it's A over 1 minus I essentially. And this simplifies to 9 over 8 times by 2 take pi over 2. The next situation is where we've got unequal radii. So if I go back, here we'd have C2 and C3. Those don't have equal radii. C4 and C5, etc. So we follow the same steps. So we've got R1, which is 1, and R3, which is a third. So finding out what cos theta is again, we've got 1 take away a third over 1 plus a third, and therefore we'd end up with theta equaling pi over 3. So R2 then will equal 1 plus a third times by the square root of 1 times by a third, take away a half times by 1 squared take away a third squared times pi over 3, take away pi over 2 times by a third squared. So essentially what we've done here is worked out the trapezium, sector 1 and sector 2, and took them away from each other. So let's continue to work all that out. Well, here I'd have 4 over 3 times by 1 over root 3, take away a half times by 8 over 9 times pi over 3, take away pi over 2 times by a 1/9. So if I continue simplifying, we'd have 4 root 3 over 9, take away 4 pi over 27, take away pi over 18. So I've got 4 root 3 over 9, take away 8 pi over 54, take away 3 pi over 54, which simplifies to 4 root 3 over 9, take away 11 pi over 54. So that's what R2 is. So the area R4, using the same idea, where we've got the area scale factor of a ninth, that's going to equal a ninth times by R2. So I've got a ninth times by 4 root 3 over 9 take away 11 pi over 54, and R6 will equal a ninth times by R4, so I've got a ninth times by the result shown here. And simplifying, I end up with 1 over 81 times by 4 root 3 over 9 take away 11 pi over 54. And we could continue. But the point is, the sum of the even terms, again, would have a over 1 minus r. So I've got the first term, 4 root 3 over 9 take away 11 pi over 54, over 1 take away the common ratio, so 1 take away a ninth. So I've got 9 over 8 times by 4 root 3 over 9 take away 11 pi over 54. So the total area will be the odd plus the even. So I've got the odd, 9 over 8 times by 2 take away pi over 2, and the even, 9 over 8 times by 4 root 3 over 9 take away 11 pi over 54. And I could continue, so I've got 9/8, and if I factorise that out, I've got 2 take away pi over 2 plus 4 root 3 over 9 take away 11 pi over 54. So if I simplify inside the bracket, I'd have 2 plus 4 root 3 over 9 take away 38 pi over 54. And if I continue to simplify, I'd have 9/8 times by 2 plus 4 root 3 over 9 take away 19 pi over 27. And multiplying the 9 over 8 into the bracket, I'd have 9 over 4 plus root 3 over 2 take away 19 pi over 24. And if I write all that over a common denominator, I end up with 54 plus 12 root 3 take away 19 pi over 24, which is the final answer.